Okay. Good. Thanks for reminding. Furkan, was that you? Okay, Mustafa. Okay, thank you, Mustafa. Um, we said that segmentation is another way of making this abstraction, but in fact, segmentation is not an alternative to paging, as we talked last time. Let's talk about this and let's finish up with the memory chapter. Okay, so far the memory for us is a one-dimensional address space. It starts from address 0 and it goes to some maximum number, whatever it is. Okay, but for many problems, having such a structure is too difficult to deal with. For example, if you have a large array, you use that large array. And later, if you like to make that large array even larger, then you need to allocate somewhere else, more space somewhere else, and copy the whole thing and get rid of the old large array position. So this is expensive, this is time consuming, complicated. Instead, segmentation says that from the hardware, from the operating system, I can help you with this. If you like, you may put your array in a segment of its own, in an address space its own. And if you like, I can make this address space larger or smaller. Okay, you don't have to do anything about this, and I will manage this. I will manage this in an efficient way. And by doing this, it is not doing any copying and that kind of allocation, deallocation stuff. So segmentation is good. Actually, we have seen a form of segmentation with the separation of instruction and data space. Remember, that's what we said. We said that if we separate the instructions and data, that would have some nice properties, like instruction space is not modified at all, so it can be shared more freely, and data space it is not that easy to share the data space, but there could be some options that we said that, right? So segmentation takes this idea and makes it further. It says that okay, if this is your program, in your program, if you need a symbol table and this is a compiler. Okay, by the way, this program is a compiler. For the compiler, you need a symbol table, source text, constant table, parse tree, call stack, etc. And each one can grow and shrink. Okay, so growing and shrinking is difficult to handle. Why? Because if my parse tree grows larger than this part, okay, the part I am showing, then I need to do what? I need to do move the call stack up and parse tree move a little bit up, etc. Instead of doing that, the solution is this. Okay, I ask the operating system to give me a linear space for the symbol table, a linear space for the source text, and linear space for those. And later I can change my decision and make these smaller or larger. Again, these are all handled by the operating system with the help of, of course, hardware. Without the hardware help, paging or segmentation is not an easy thing to do. That would be too slow. So we need hardware help for segmentation. Okay, I think that's what we said last time. That's what we said last time, and that's the positive part of the segmentation. Let's look at the segmentation in terms of operating systems, how they use it. Okay. So segment is a logical entity. What do I mean by logical entity? The users, programmers, they know about the segments. Okay. Previously our only logical entity regarding the memory was the only address space, the only linear address space. That was the only logical entity. Now we have more than one segment. we may have as many as we like. We may have more than 1,000 segments in our program. Okay, so the programmer is aware of the situation, and it says that the programmer says that I will use this segment for this purpose and this purpose and this purpose. So this, for the segmentation, as a user, I need to know about it. Remember, for the paging for the virtual memory, the user doesn't know anything about the pages. The user doesn't know anything about the page replacement algorithms or the translation look-aside buffers or the inverse hashing or etc. Okay, they are all handled by the operating system with the help of the hardware. Segmentation, of course, needs the hardware help, but the user of the system, the programmer, needs to know about the segments so that he or she can say that, okay, I have my 5 segments, okay, each of these segment, and this segment is doing this, and this segment is doing this, and this segment is doing this. Okay, so a segment, it is up to you. What are you going to do with the segments? You may store your code in the segment, an array or stack, or your constant variables, doesn't matter what they are. Or you may you may put your shared libraries in the segments. Okay, let's say you have a separate segment somewhere here. Let's say I have drawing with the red, drawing with the, now I changed my mind, drawing with the blue. I have a new segment, okay, and this new segment I have stdio function. So at the beginning of the segment I have printf, then let's say scanf, etc. So this segment, I always know where printf is, where scanf is, and they don't have to do position independent code. The code could be position dependent because for the printf, the starting address and end address is always the same. And this segment, it could be a shared segment that could be shared by any process that are interested in using the stdio functions. So the segment could be anything like that. With the shared segments, it becomes very, very powerful. Okay, good. So what did I say? I said that if you like, you may have a segment for anything. You may even do this. For each function, for each procedure, you may have a separate segment. For printf, there is a segment. For scanf, there is another segment. For file open, there is another segment. You could do that. You don't have to worry because the CPUs are good enough to they can provide us with thousands of segments if you like, and that's not going to make our program slower. Okay, that's not going to make our program slower. We are going to see it in a few minutes that segmentation is part of the addressing structure. Okay, so you can make each of these segments easy, larger or smaller, doesn't matter how you deal with them. It will be handled by the operating system. Okay, so this is what I am saying. The book says that a shared graphical library can be put in a segment and shared by multiple processes, eliminating the need for having in every process address space. So remember we said that sharing pages was good. Remember that? But with the sharing pages, there was this problem of position independent code. With the segmentation, there is no position independent code because all the code assumes that I am in a segment of my own and I know the addresses and I don't have to do relative addressing. Everything can be done. Okay, any questions so far about the segmentation? Any questions? Okay, then if there are no questions, then I will continue then. İlhan, are you there? Can we start the attendance?
Yes, sure, Professor.
Okay, thank you. So this is kind of a nice comparison table between the segmentation and the paging. Doğancan has a question: would increasing the number of segments increase the page faults? Well, with the segmentation, you don't have the page faults anymore because let's look at this picture, okay? That's a good. Okay. With the pure segmentation, there is no paging. Okay. With the pure segmentation, there is no paging. So that means that the operating system has to put all the required segments into the memory. Okay. Into the memory. So if you are addressing something out of the segment, then it's a segmentation fault, and that segmentation fault is a fatal problem actually, and your program needs to be terminated. There is no page fault with the segmentation, with the pure segmentation. Okay, so but it turns out that we need paging with the segmentation. In that case, each segment, like I told you last time, let's look at this segment 3. Okay, I said that the segment 3 will have 4 pages in it. Okay, 4 pages in it, and if I need, I will bring in and out the pages from my memory, no problem. From my memory, no problem. And that will be paging with segmentation with paging. If I do it this way, if your question is, if I use paging with segmentation, would it increase the page faults? No, why should it be? Because I have the principle of locality again. Okay, most of the time my program will work with a working set, and if that working set, pages of working set, is in my memory, then I will not have any page faults any more than the regular paging anyway. Okay, so it will not increase any page faults. Okay, so the nice thing about the segmentation is it makes the job of the programmer easier by giving you more logical spaces. You don't have to deal with one single large linear space. You have many linear spaces, and you may call each one something different. Okay, so I talked about this, and library we talked about this, and this is the nice table that we are talking about. Okay, the attendance out. So I think you have a few minutes. I don't know. Just fill in the attendance. Okay. So this is the comparison table, nice table from the book again. It tries to compare the segmentation with the paging. So the first one is important. Okay. It says that the programmer be aware that the technique is being used. For the paging, no, of course. The programmer would think that, okay, I have my CPU, I have my memory, I can do whatever I want, okay, with the CPU and memory, no problem. But for the segmentation, the programmer has to tell the operating system that for this program I need 5 segments, okay, and for these segments, this one will be read only, this one will be this, and this one will be that. And if you are paging your segments, then you need to tell that too. I need these segments to be paged. Okay. So how many linear address spaces are there for the paging? There is only one large linear space. Okay. And for the segmentation, there could be many as thousands, tens of thousands. Okay. Okay. Can the total address space exceed the size of the physical memory? Yes. With the paging, that was one of the original ideas, right? I mean, I can have programs that are larger than my physical memory. For the segmentation, okay, even without paging, you may keep some of the segments in your memory and some of them are not in your memory. Okay, this is different from overlays. Remember overlays? Okay, in the overlays, the programmer would say that this part of the program will stay in the memory and this will not stay in the memory. With the segmentation, I don't care about that. Okay, let's say I have 10 segments. Whatever segments I am using, they will be used and they will be in the memory. The others will not be kept in the memory. So with the segmentation, of course, the total address space can exceed the physical size of the memory. Okay. So the fourth one is, can procedures and data be distinguished and separately protected? For the paging, it is not possible. They cannot be separately protected. Because the programmer doesn't know about the paging, the programmer cannot say that this page will be data only, this page will be code only, this page will be write and read and etc. No, but with the segmentation, yeah, I can do that. Okay, can the tables whose size fluctuates be accommodated easily? With the paging, no, you have to do it yourself as a programmer. You need to allocate space, deallocate space, etc. For the segmentation, it is done automatically by the operating system and the hardware. Okay, and is sharing of procedures between users facilitated? This is not exactly a no. Actually, this is yes and no. Remember, we said that with the paging, you could share pages between the users. Okay, that's how the DLLs are done. But if you are using paging with the shared code, okay, in that case your code has to be special. It has to be position independent code. With the segmentation, I don't have any restrictions like that. Okay, I could say that this procedure has its own segment. Okay, so why this technique was invented at the end of this page? Okay, for the paging, remember that was the very good way of getting large linear addresses without having to buy more physical memory. Your program doesn't have to fit the memory. Some part of it could be outside of the memory. They could be in the disk. Also contiguous, remember the contiguous memory. So the paging doesn't require your program to be stored in a contiguous way. What do I mean by it is not doesn't have to be stored in the contiguous way? You may change your page orders, right? And it is also flexible by the configuration of the page table. So this was one of the main points of the paging. So why did we need this segmentation? It is there to allow programs and data to be broken into logically independent address spaces, okay, and to aid sharing and protection. That was the idea. So as I said before, segmentation, pure segmentation by itself is seldomly used. It is usually used with paging. So whatever the paging has the advantages, they will be the advantages of segmentation. Okay, so let's look at the so if this is the implementation of pure paging, okay, if I have 5 segments, okay, if I have 5 segments at the beginning of the program and later I added new segments and I deleted some and etc. So I have this space that I am marking with red pen being available empty in my physical memory. Okay, this is called fragmentation, or some people they call this checkerboarding. Some people they call this checkerboarding. Okay, some part of the program, some part of the physical memory is not used, and since the segments have to be contiguous, then I need to move segments around. I need to move my segments around. Moving the segments around is not that difficult because segments have their pointers. You just change their pointers, that's it. Okay. Of course, you need to copy the data from one position to another position. That's not going to be good. Copying is bad. Okay. I mean, we said that this is inefficient. The programmer doesn't do the copying. Operating system does it, but it is not good. So this compaction is a problem. Compaction is a problem for the segmentation. So maybe they should have another line at this table which says, okay, needs compaction, okay. For the paging it is no. For the segmentation it is yes. So it is one of the disadvantages of pure segmentation. Okay. So by running this compaction from time to time, you need this space to get this space so that it is usable now. Any segment that needs like 8 kilobytes will be okay. Okay, so this is the pure segmentation. As I said, we don't do pure segmentation. We do segmentation with paging. Each segment is paged. So instead of showing a hypothetical system, let's look at a real system, Multix. Okay, remember Multix? We talked about Multix a lot. We talked about Multix when we talked about time sharing. Okay, and we talked about Multix when we talked about translation local-side buffers. So Multix is a very influential operating system invented in 1960s. It took some time to develop it. Okay, it had many, for example, Unix. Okay, when people started working on Unix, they said that Multix is too big for our computer. Okay, so we are gonna make a smaller version of it. So, but to make it a funny name, they choose the name of Unix. Okay, so because they don't have any plans for having multiple users, Unix. Okay, so Unix kind of tries to emulate Multix, but it eliminates lots of features of it, like multi-users, time sharing, etc. Okay, so this Multix structure, of course, when they develop Multix, they are developing the hardware too. So it had great significant effects on the Intel architecture. Okay, Intel architecture used the Multix ideas. Translation local-side buffers are invented by Multix. Time sharing is Multix invention actually. And cloud computing, and the cloud computing was the main idea. They said that let's have one large computer, let's have one large computer at a computing center, and let's give users, home users, terminals. Okay, and these terminals will be connected to this large computer, and they will use it. So this is the definition of cloud computing actually. Okay, so the project took lots of time to implement because they had the home users, they needed commercial help, lots of money. So it went live in 1969. The same system, same Multix system, okay, was running until 2000. So a total of 31 years. Okay, total of 31 years. That's a lot of time for a operating system. No other operating system like this have been used for such long. You may say that, okay, Windows, we are using Windows for the last 30 years, 40 years maybe, from 1990s to 2020, but Windows, only the name stayed the same. Okay, Windows 3.1 is very different from Windows 10. Okay, they are not compatible. They are not the same operating system. They are only their names is the same. For the Multix, it was the same system. So when they shut down the computer in 2000, it is not because Multix was not enough for their tasks. It is because since Multix is developed with the hardware, nobody provided them with the required hardware for Multix. That's why. So they couldn't find the necessary hardware components for that computer to run. Okay, so let's go back, and that's why always read about Multix. There are very nice documentaries. Remember the documentary that I showed you about the computing bottleneck? They say that we have a large computer and nobody is able to use it efficiently, so we invented time sharing. So it was always it was always it was always it was always what happened? Okay, it was always did my okay good. It was always possible to use that computer in a way, but they wanted to make it more efficient, and they were talking about it. And even 1960s, 1970s, that was a problem. And those people are always talking about it. Just read the literature, watch those movies, and you will understand what they were thinking, and the problems are actually the same. So let's look at the segmentation structure of Multix. Okay, with the Multix, this is our virtual memory. Okay, this is how the virtual memory is. For each program, okay, for each program, I have a 36-bit descriptor. Okay, so that means that I can have 2 to the 36 segments. Okay, and each program can have as many segments as they like. So the number of segments is very, very high, if you like. Okay, from this segment descriptor, you get a pointer for a page table. Okay, so this is what I mean by each segment is paged. So each segment is a linear space, but that linear space is paged. So I get the page table for that segment. Okay, so I have this many 2 to the power 36 segments, and each segment will have their own page tables. So this is not pure segmentation, of course. This is a segmentation with paging. But if you like, you may tell the operating system that I want by segment, not paged. Okay, it is possible to, and we will see in a few minutes. Okay, so this is the Multix virtual memory. Okay, this is the Multix virtual memory and the segment descriptor. Okay, segment descriptor, and there should be, okay, this is 20, so this is 36 bits, and inside this, okay, 36 bits, this is what we are gonna see when we look at one of the descriptors. So 18 of those descriptor bits is the address of the page table. If I am a segment, okay, if I am a segment, then this address is my page table. Okay, so how many page tables could there be? Then there could be 2 to the power 18 page tables. So it is like 256,000, right? 256,000 page tables. And then after that, okay, so this is actually this pointer. These red arrows that I am drawing, these red arrows that I am drawing are the page table pointers, and those arrows are represented by these 18 bits. Okay, so each segment should know its starting address in the page table, and also each segment should have its length in pages. Okay, so there could be at most total of 2 to the 9 pages in a single segment. This is not 2 to the 9 bytes, okay? This is 2 to the 9 pages, okay? So the page size is another property of the segment. The page size could be either 1024 words, okay, or 64 words. That's the page size. So what would be the largest segment size in this case? So tell me the largest segment size possible in Multix. Let's say this is a segment in Multix. It starts from address 0. As I said before, it can change its segment length, but I am asking what would be the largest segment size in Multix? Anybody any ideas? I know that there could be 2 to the 9, okay, pages. Okay, Doğancan, he wrote a complete paragraph, so it took him so long then. Assume the word is 4 bytes, okay. We have some maximum segment length times page size times word size. That's very good, yeah. 2 to the power 9 times 2 to the power 10 times 2 to the power 2 is like 2 megabytes. Yes, okay. Okay, so that's the idea actually. That's the idea. So it is 2 to the 19 actually, 2 to the 9 pages, and since each page is 2 to the 10, so there could be at most 2 to the 19 words. Okay, 2 to the 19 words. And Doğancan says that let's say the words are 2 bytes. Actually the words are 32 bits actually. 36 I guess. So it's kind of a weird structure. So let's look at this field, this one that I am pointing now. I am waiting for 4 seconds. Segment is paged, segment is not paged. So if you select this as 0, then this segment is not paged. So the paging is disabled for that one. So whatever you get is directly your continuous memory. Okay, and there are some miscellaneous bits, and the book doesn't talk about it, and there are protection bits. Is this segment readable, writable, executable, etc.? Okay, so this is the structure of Multix segmentation, and this is this 36 bits. Is this 36? 28, 9. Yeah, this is total of. There are total of 36 bits in this descriptor. Inside this 36 bits, I have the segment start address, segment page table entry, page table, and the length of the segment, and etc. I have all of these. So this is my virtual address structure actually. Each time I make a memory reference, okay, each time I make a memory reference, I say, okay, this is my segment, okay. No. What I'm saying is not correct. This is just a descriptor. This is just a descriptor. How we do the virtual addressing is like this. Okay, this is the virtual address. Okay, your virtual address is okay. 28, 34 bits, right? At the beginning you have 2 to the 18 segments. Okay, then you will say that inside that I will have my page number 2 to the 6 page numbers. Okay, then I have pages in it. Okay, 2 to the 10. So each page is at most, as we said before, 1K. Okay, and this is my page number. Remember we said that there could be 9, 2 to the 9, right? There could be 2 to the 9 pages. So how am I going to address this? I mean, Multix was a very complicated system. Since I had this option of having 2 different page sizes, 0, 1, okay. So if your page size changes, your virtual addresses changes. So this picture does not represent all possible addresses. Okay, so this is just for the 1 kilo word pages. Okay, and this is only valid with the segmentation with paging. So this is a typical Multix address is produced this way. Okay, so that was the picture with the Multix, and then this is what you do. You get this 18 bits. You get your segment number. From the segment number you get your page number. Okay, from the page frame you get your page in your physical memory. Of course, this is done with the help of the hardware. Memory management unit does all these things for you, because this is done every time when you reach the memory. Okay, so the memory management unit does that. But to have this kind of memory inside the memory management unit is too expensive. Then they had to invent what since this is too expensive to fit into the memory management unit, I cannot put 2 to the 18, okay, 256 kilo words of data in my memory management unit. Okay, so what am I gonna do? I will have to invent now what? Okay, assume that you live in 1960s. Nobody went to the moon, and your segment table is too big to fit in your memory management unit. And in fact, there are no memory management units. You have to invent that too. Assume that you invented memory management unit. Then you said that no, I cannot fit this 2 to the 18 words in my memory management unit. What am I going to do? Either my programs will be very, very, very slow, like 10 times slow, or I will find a solution. What's your solution? Somebody's typing. Well, I mean, I don't want you to find the solution. I want you to tell me the name of the solution, because we have seen it. We had exactly the same problem with the paging. TLB, exactly, Beza. Okay, TLB is the solution. It is invented by Multix. So, in fact, with the TLB, the Multix has only 8 TLB registers. Instead of having 2 to the 18 words in the MMU, it has only 2 to the 3. Okay, so due to the principle of locality, And well, it looks like they know about the principle of logarithmy. This idea will work. So this is the structure of the simplified version of the Multix TLB. This is more complicated. It is actually more complicated than this because it has two page sizes. One is 64 words. The other one is more than 1000 words. So, but it is simplified. So what you do is, this part is important. This is when you do the comparison. Whenever any virtual address is produced, okay, you get the segment number and the virtual number, and you compare them with all the numbers in this part of the table. If it is there, then you have a hit. You get the page frame number, you get this protection, and you have this page. Page is for replacement, okay? Replacement in the TLB. And this is valid, invalid bet at the end. Valid, invalid bet. Okay, so this is segmentation with paging with Multix, and Intel was very influenced by this idea, and they used a very similar idea with the Intel architecture, and we used this for a very long time. So when Intel introduced this 64-bit structure, okay, they gave up using this segmentation idea. They are using this pure paging. There are some other things that can behave like segmentation. Segmentation is still possible with the 64-bit Intel structure, but it's in legacy mode. It's just compatibility mode. Okay, so I am not going to look at the Intel architecture, but it is similar to Multix idea. Okay, well, there are, remember, we had 2 to the 18 segments. There are so large a number of segments available. With the Intel structure, no, we don't have it that way. Let me try to find it. Okay, there are only 2 to the 13 segments, not many segments. Well, 2 to the 13 is not bad actually. 2 to the 13 is 2 for 8 kilo, right? 8K segments. For each program, they can have their 8,000 segments, more than 8,000 segments. But each segment can have very large amounts of linear space. So I will not talk about it, but the idea is the same. You get your segment, you have your base address, limit address, other fields, and you have your 32-bit linear address. Okay, so it looks like, yeah, okay. So this is 2 to the 10 due to some limitations of segments, and inside each one there will be, okay, each page table there are 2 to the 10 page table entries, and I have 4 kilobytes page sizes. Intel can change its page size too, okay, but 4 kilobytes is kind of the norm. We used a lot, 4 kilobytes. Okay, good. Any questions about virtual memory? Well, virtual memory, as we stressed many times, is important. Without abstracting the memory, there is no way I can fit more than one program in my memory. There would be no protection. So with the operating systems regarding the memory management, so I need to be able to fit more than one program in my memory and provide protection, okay, provide abstraction to the program so that they think that they have the whole memory as a linear space or the number of segments. And we do these kind of stuff using these techniques called paging and segmentation. Mostly paging is used. And the programmer, as a programmer, you never know about the paging. You never know about what's going on with the memory or the memory management unit and etc. You don't care about it. It's very similar to the processes. With the processes, all you think is that I have my CPU and I'm running. Okay. That's remember, what does the operating systems do? Let's ask that question. It says that, okay, it says that I will abstract the hardware, details of the hardware will be abstracted away, and I will manage the resources. Resource management. Okay, two things. Okay, that's what we did with this chapter regarding the memory. I abstracted the details of the memory. Memory is not very complicated space, but when you do the paging and segmentation, it becomes complicated. Nobody knows about those as users. Also, the resource management, the memory has to be managed. It has to be allocated. It has to be shared among the processes, between the processes. So these are all done with the operating system. Beza has a question. It's a nice question actually. Is the segmentation with paging same as multi-level paging? No. Because with the multi-level paging, again, the user doesn't know anything about the paging. The user would think that I have a very large memory space. It starts from address 000. It goes to address FFFF, very large number, right? With multi-level paging, okay, since for large memories and large table sizes, tables are so large, I decided that maybe I should do it in a hierarchical way, okay? So that was an idea to save memory space. So the user doesn't know anything about the paging or multi-level paging. With the segmentation, the user knows that, okay, the user of the program, Intel program, knows that the first 10 bits of your address will be your segment number. And that segment number will tell me if that segment is going to be a executable segment or the read-only segment, data segment, symbol table segment, and etc. Okay. So this picture really looks like a multi-level paging picture, but in fact, it is not. Okay. In fact, it is not. And actually, Beyza, that's a very nice. Midterm exam question. Let me copy. Let me copy and okay, paste it to my exam questions. Oh. Did you guys see it? Anyway, okay. So I have recorded my midterm exam question possibles. Okay, good. Okay, good. So I am not going to erase that part out. It is recorded, and you can check it out. Okay, so that's a nice question. So it is different. No, it is definitely different. This on the user knows about this 10 bits. Okay, for the paging, whether it is multi-level or single level, it is always the user doesn't care about it. User would think that it's a regular address. Okay, good. So let's take 10 minutes of break. After the break, we will start talking about file systems. Okay, let's continue with chapter number 4, file systems. So far, we studied operating systems. Generally, we overviewed the whole operating system in chapter number 1. Chapter number 2, we abstracted away the complications of the CPU in terms of sharing the CPU with more than one process. We invented the idea of, with chapter number 2, we invented the idea of processes. Okay, that's the abstraction method. In chapter number 3, we invented the idea of virtual memory or address spaces. Okay. With the chapter file systems, okay, we will deal with the issues about the secondary storage, and now we will abstract the complications of the secondary storage with the idea of files. Okay, so files are the third important concept, abstraction method, that we're going to use to study operating systems, also designed operating systems. I mean, if you compare files with processes or the address spaces, I think this is the most familiar one, because starting from the C programming language courses, we opened files, we created files, we read files, we appended files, etc. We know how to use files. Previously, we did not have any process creation or the virtual memory address in any of our classes, but the files, we are familiar with the files. But the thing is that in terms of studying operating systems, how the files are implemented, how they are manipulated by the operating system, we don't know about them, and this chapter mostly will look at that issue. Okay, let's look at the files then. Okay, so far we said that, okay, our processes start, they use the memory, they do their computation, they store their values somewhere, but okay, if the data that I am dealing with is too big, okay, I cannot fit in my main memory, so I need to get help from some secondary storage. So it must be possible to store very large amount of information other than my main memory, okay, the memory that is connected to my system bus, okay. And the other thing is that once my process is terminated, all the memory used by my process is gone, right? It is all discarded by the operating system. It is not saved at all. So what happens to my computed values, manipulated values? I need to have one way to make them permanent, okay, make them permanent on some other medium, which will be my secondary storage again. So information must survive termination of process using it. And the third one is the processes must be able to access information concurrently. I mean, the same data on my secondary storage should be available to many processes at the same time or different times. So it's also shareable. So these are the essential requirements for my long-term information storage, secondary storage. Okay. So to solve all of these problems, I come up with the idea of files. Okay, and we will talk about files in this chapter. The idea of file is very simple. Actually, remember the idea of virtual memories was simple too. I mean, as a user, I don't need to know anything. Okay, I don't need to know anything about the paging or segmentation or the TLB buffers and etc. The files will be the same. File will be an abstraction method for me. All I care is when I open a file, it's a linear space and etc. That's the idea is going to be very, very similar to the virtual memory. Okay. So let's go ahead and let's try to follow what the book says about the files. Okay. This is what I said before actually. I said that process was our first abstraction. Operating system abstracted away the concept of processor, and then we abstracted the complications of the address spaces like that. Okay, with the so our new abstraction is going to be the file. And in fact, if you know the abstractions, processes, threads, okay, these are kind of the same thing, address spaces and files, then that means that you are becoming a very good operating system expert. Okay, so if you know these three things about an operating system, you know about the operating system very well. That's the first thing. The second thing is that you are becoming a good operating system designer, okay, operating system expert. And if you like to study a new operating system, just study these. What kind of processes can I have or threads can I have? What is the address space? What kind of file system they are supporting? These are the important things about the operating system. The important things about the operating system as a programmer, as a computer engineer are these. As the end user, maybe it is the as the end user, maybe it is important to have what kind of interfaces I would have with the operating system. That's true too. But as a computer engineer, okay, as a system programmer, maybe the important thing here is these kind of concepts. So Kamil has a question. Kamil says that are we talking about serial ETA? I will talk a little bit about it, but no, we will not go into details of it. And in fact, I will not talk about those kind of devices in this chapter. No. File systems are about how the files are structured, how they are implemented. Okay. Serial ATA, okay. SATA disks, they are the topics of the I/O chapter, which is the chapter just after this file systems. Okay, so the secondary storage devices are actually input-output devices, and we will look at them separately. But I will not go into details of it. I mean, if I had to go into the details of disk structures, different disk devices, then I will have to go into different display structures or the mouse structures and that kind of stuff. So I will not do that. Okay, so not in detail anyway. Not that because they are not important. They are important, but we don't have that kind of schedule for this course. Okay, so let's learn these three stuff. Okay, then you are a good operating system expert. Good. So the idea of files, as I said before, is very simple. For a user, for an end user, for a programmer, okay, you make a file, and inside your file there are blocks. Instead of words, remember in the memory world it was the words, okay. Now I have blocks. Block number 0, 1, 2, 3, 4, etc. It goes that way. So what you do is you just read block number K and write block number K. That's it. Okay. So the size of the block changes from system to system. Okay. From configuration to configurations. Sometimes each block might be a single byte. Most of the time Unix systems support this. So you read your files byte by byte, okay, or write them byte by byte, right? So as an end user, this is my view of a file. This is my view of a file. It is very similar to memory. Of course, to be able to read or write to a file, I need to first open it. If it is on my secondary storage, it is not there, then I need to create it. Okay. I didn't have this kind of stuff with my memory. With the files, you have to do that. Okay. So two operations, write, read. Okay. That's what we did with my memory too, write and read. Okay, so how am I gonna give this abstraction to the end user? Okay, by not forgetting about these three long-term requirements. Very large amount of information. That's one thing. Survive the termination of process. That's another thing. And sharing of the data inside the file among the processes. That's the third thing. So provide this abstraction by always keeping those three requirements in mind. So we will talk about this a lot. But before we go into how we implement these kind of structures on hardware, we will look at the files and file systems as an end user, and we will try to remember what we were doing. Okay. So the questions are: how do you find the required information? By just indexing. Okay, if I access the Kate block, is it good enough? Okay. The second thing is that, again, like the memory or the CPU, how am I gonna provide protection? Okay, how am I gonna provide protection? Keep one user from reading another user's data. How am I gonna do that? That's the second thing. And third thing is, how do I know which blocks are free? On my desk, okay, on my desk, this is the idea. Let's say my desk space is like this, very large space, and these are my files. File 1, and here file 2, and here file 3. So you remember this picture, right? You remember this picture. I mean, I just drew this similar picture with the segmentation, with the paging. There are some empty spaces in my memory, and there are some available spaces. And how do I keep this information? How would I know which blocks are free? How would I know which blocks are used by whom? Okay. And while I am doing this, don't forget this has to be. Don't forget that this has to be long-term storage. I mean, if I mess up my memory, if a process messes up its memory due to some bug, okay, my process started running. It ran maybe for 10 hours. After 10 hours, there was a bug, and it messed up all of its memory. Everything is junk. So what would I do? I would restart my process from the beginning, right? With the files, I cannot do that, because if once they are messed up, I lose data, because that data is supposed to be long-term data. You are not supposed to lose it. Okay, so the problems becomes kind of different. I mean, there are some common problems that we have seen with the memory, and there are some new problems. Okay, so and these are our design decisions with the files. Okay, as an operating system designer, I need to make decisions on file names, how long the file name should be, okay, or what kind of characters can I use in the file names, structure of the files, okay, should it be hierarchical or non-hierarchical, okay, that's the decision. And the types of access control: read-only files, write files, files with enough permission, etc. Versioning is important. I mean, I don't keep a single copy of a file all the time. I keep versions of it. The version number 0, 1, 2, 3. Some people still work on the version number 1. The other people may work on version number 2, right? Okay. So fault recovery. We never had anything like this with the processes or the virtual memory. We never had anything like this. Okay, we don't have any versions of memory. Once the memory is erased, it is erased. I don't keep old versions. Fault recovery, again, I mean, if a process crashes, it crashes. Okay, but if a file is crashed, it is not. If the file is not recognizable anymore, what should I do? Maybe I should have some kind of a fault recovery routines. Okay. So Ali Haidar has a question. File systems do the protection, so does it mean that there is no need for critical region for file accessing in the... Okay, so how about the critical... Well, Ali is bringing up a good point. Are you going to have race issues, race conditions with the files? Okay, if you have more than one process, okay, manipulating, reading, writing the same data, it is always possible to have race conditions, yes. And if there are race conditions, then there should be some critical regions. Okay, so file systems do the protection, yes, that's true, but protection is not for race conditions. Protection is for other people not being able to read or write the other people's data. Okay, so it is the permissions. So we need to be careful about race conditions when we manipulate the same file positions between the processes. So it is not going away, and protection doesn't solve it. But if you say that each process has its own files, okay, and nobody can access the other processes' files, then that will solve the whole race condition problem, right? Because nobody is sharing any data. That would solve the problem of having the race conditions with the memory or the processes too, because if you stop everybody from sharing data, there will not be any race condition. But we don't want that, right? From time to time, we like to share data. Otherwise, the processes cannot help each other. We like our processes and threads helping each other. Okay, then we will talk about file operations, regular operations, like we know all of the file operations actually. We know opening files, creating files, closing files, reading, writing files, appending files, etc. And there are many more design decisions, and we will get them from the perspective of both the end user, also the operating system designer. Okay, good. So let's start from this file names. Remember file names? Let's start from the file names, files and file names. Okay, again, file is an abstraction mechanism. It abstracts away the details of how I store that information as a linear space on my secondary storage, whether it's a disk or solid state drive, doesn't matter. Okay, and it provides a way to store information on the disk. When I say, okay, in this chapter, when I say disk, I mean secondary storage, because I don't have to use disks to keep my data out of memory. Okay, but usually disks are the norm. We usually use this term disk. Okay, when I say disk, it means secondary storage. Okay, so to be able to make a file, read a file, write to a file, I need the file names. I didn't have any memory names problem before. Okay, all I had was the one large linear memory space. Okay, that was the idea of virtual memory. But with the files, I need to have file names, because the data stored in each file might be very, very different. Maybe, I mean, it is not exact fit, but you may think file names as the segments of the segmentation, right? So remember, what did the segmentation do? Segmentation divided my memory into many logical linear spaces. Files are kind of doing the same thing. Files are dividing my secondary storage into many different linear storage spaces, and each one has a name. Okay, each one has a name. With the segmentation, each segment has its own number, segment number. With the files, they have their names. Okay, and file names, of course, there should be some rules for the file names. Some systems they say that I am case sensitive. Okay, this file is different than this file because capital A and small case a are two different letters for me. Okay, that's one thing. Okay, I need to be careful about it, and as an operating system designer, I need to make decisions about that one. Okay, usually the Windows and DOS-based systems, they don't care about the case, but in Unix they are different. Extensions. Okay, this is an extension .txt. Okay, some systems say that extensions are not permitted. You are not allowed to have permitted. Some systems say that extensions are permitted, but I don't care what they are. I just uninterpret them. Okay. Some systems say that extensions are required. You need to have extensions. Without the extensions, I cannot know the type of the file. Okay. The other one says that, okay, extensions are allowed, but you may have at most 3 letters in the extensions. Okay. So again, these are the differences between the files. And I have the character set. Some systems say that I will use only ASCII characters. I will use only ASCII characters in my files, file names, not files, but file names, character set. The others say that no, it is possible to use Unicode characters. So a file named this is possible. Çözüm.txt is possible. I have letters that are not in the ASCII set. Okay, so some operating systems force you to have uniform file name schemes, like the 3-letter extensions, at most 8 characters, and etc. Some of them, they don't care. Okay, they say that, okay, file names is something up to you. You may use any file names that you like, no problem. So files and file names are one of the design issues that the operating system designers has to decide on. And we don't know that many operating systems, actually. I mean, all we know is the Windows operating system and the Unix operating system. Linux is a variant of Unix. Apple operating system is a variant of Unix. Okay, Android is a variant of Unix or Linux. Okay, so we know about them. And Windows file naming rules and the Linux file naming rules nowadays are very similar. But previously, DOS, okay, before Windows NT, okay, there were several restrictions about the file names with the DOS side. You could have at most 8 characters as the file base name and the 3-letter extensions. That was the rule. Okay, good. File systems, they are part of the operating system. They are like the virtual memory system or the thread manipulation system. They are file systems. Okay, they deal with the files. Okay, they manage how the files are created, opened, read, manipulated, etc. That's the part of the file system, and that's one of the main parts of an operating system. If we go back to the first chapter of the book, can I go there? Let me try to open it. Yeah, okay, here it is. So when I say what's an operating system, I'm trying to remember where was that thing. There was a very nice structure of an operating system. These are the history stuff. Always read the computer science history and always read the operating system history from time to time. Every time you read it, you will notice that you did not see that in the first time. I'm trying to find the main logical structures of the operating system. These are the types of the operating system. Are there spaces? No, I did not see it. I don't know. Okay, anyway, I can draw it myself. Okay, so this is our hardware. Okay, this is our OS kernel. Inside the OS kernel, I should definitely have my scheduler for the processes. Okay, and I have my memory manager. Okay, and I should have my file system. Okay, so the file system is important part of the operating system. It's an important part of the operating system that deals with the files. It's like memory manager, but these are file systems. The difference, one of the main differences from the memory manager is that there could be more than one file system on my computer, because you may have more than one secondary storage input-output device connected to your computer. One would be a rotary disk, hard disk. The other one could be a flash drive. The other one could be solid state drive. The other one could be a tape drive, right? And the other one could be a CD-ROM. Okay, each one has a different file system, and to be able to abstract away the details of files on each system, I need to have a different file system. Okay, here are a number of file systems that we use commonly. File access table, FAT16. This is one of the oldest file systems, and it is being used a lot actually. I mean, nowadays this one is being used a lot because it is very simple and it is compatible, since it is used by many systems like the entertainment systems, small devices, right? When they store files, they use FAT16. Okay, so if each small device uses FAT16 to manipulate their files, then their files will be compatible between each other, right? So that's why it's very popular. And as the name implies, this is for 16 bits, and we will see why it is 16 bits. This is FAT32. They said that 16 bits is not enough to keep all of my data. This is not large enough. So let's do this 32 bits. This is large enough now. Windows 98 introduced it. And I have NTFS from the Windows. Okay, NT. It's a compatible file system with lots of features. Then we have resilient file system with lots of recovery capabilities. And we have this XFAT, like the FAT. Okay, this one is good for flash drives or large file systems. So there will be many different file systems, and your operating system may not support all of them at the same time, but you will see some of them from time to time. If you look up Wikipedia, okay, file system types, there is a very nice list of file systems available there. Okay, so this is talking about it. List of file systems. Didn't I see it? Yeah, okay, so it is talking about the file systems of different operating systems. For Windows, I have the FAT file system, NTFS, EXFAT, etc., resilient file systems. No, I was looking for a list. Okay, list of file systems. This is better. Yes. Okay. So this is the list of file systems. It's very long list. It's alphabetically ordered. And these are EXTs, extended file systems. They're the Linux operating systems, file systems. And they keep changing it. They keep adding more and more stuff. Newer file systems doesn't mean that they are the most useful, because they are sometimes expensive. Okay, so have a look at it. Some of them are very old, some of them are new. They have their own advantages and disadvantages. So what I am trying to say is that your operating system kernel might have more than one file system available. And we will talk about it. That makes it a little bit complicated to handle, but it has certainly advantages. Good. Here are remember we talked about the file names and extensions. Here are some of the extensions that we commonly use. I think you know all about them. Remember, most of them, I mean, if you notice that most of them are just a few letter extensions. And this comes from the DOS days, because in the DOS days, 3 letters are the most that you can use for an extension. But as a exception, we have this HTML. Usually during those days, some web pages has this extension of HTML, not HTML, but HTML. So if a web page has this extension HTML, that means that the server is using a file system from the old days. Okay, good. So how do I structure the files? Okay, the same question as how do I keep my information on my memory for a process? Do I keep it as a contiguous configuration? Do I keep it as paged, etc.? So I need to make these decisions. Then these are called file structures. Okay, in the old systems, this was your structure. Okay, in the old systems, since everything was based on the punch cards, remember the punch cards? Punch cards, they contained 60 characters of data for each card, right? That's why we have 60 columns on our terminals, right? And the same structure affected how the files are stored on the tapes. Okay, so files are sequence of records, and each record is an image of a punch card or printer line. Okay, so that's how they organize it. Let's say this is your old system file, and it is divided into these kind of records. Each one is a record. Okay, R1, R2, R3, etc. And this is your first punch card, second punch card, third punch card, fourth punch card, etc. Okay, so Unix and Windows, mostly Unix, they said that this is too limiting, too restrictive. I am not going to do it that way. I will organize my files as sequences of bytes. Sequence of bytes. I don't need to talk about the punch cards or the printer lines. Okay, for most applications they are not meaningful. Okay, I don't know what the punch card is nowadays, right? So all the important things are like 8-bit bytes. So it is, each file is a collection of randomly accessible sequence of bytes. Okay, there are some systems that talk about the pages, like the records. Sequence of page says blocks. Okay, so these are some design decisions, but nowadays this is the most common design. Randomly addressable sequence of bytes, because having that means that it is the most amount of flexibility. I don't have to deal with the records. I don't have to deal with the pages. I deal with the bytes, and when I combine them together, like the structs, I can put any structure that I like into my file. No problem. Okay, so these are some examples. So these are from the early days. The B, part B, is from the early days. Each record is like a punch card or the printer line. Nowadays we mostly use A. Okay, I address each part of the file by a single byte. Okay, when I say open a file, it gives me a file. When I say read, it reads it byte by byte. Remember the Unix or C read function, you say that read 10 bytes into this buffer, right? You talk about the bytes. You don't talk about records. You talk about bytes. And then we had these kind of B3 typed. Remember the B3s or B plus 3, or you remember 2, 3, 2, 3 trees. Okay, so it's like that. So you keep your information in this B3 structure on your file. That's what you do. And when you do this, it is easy to make a find. Like I am looking for lamb. Okay, I'm looking for lamb. L is greater than A. L is greater than F. L is less than P. Then I go there. L is greater than G. L is lamb is less than lion. Then I go there and I do this. I find it. So it's kind of binary search. It's not binary, of course, but it's a hierarchical search. And I like to have this structure in my file. And there were some files like this, but nowadays I like to imitate this idea using this structure in part A. Okay, good. And we are going to have lots of file types depending on your point of view. This is one way of looking at the file types. Okay, there are regular files and there are directories. Directories are actually files, but they contain files in them. So they are special files. So they are like files of files directories. Okay, and directories might contain other directories too. So they are special kind of files. So far I have showed the examples only the regular files. A file with a linear address space from byte number 0 to byte number some large number. That was the regular files. But the directories are not like that. Directories say that all I contain is the names of the other files. And each file could be another directory too. There are some character special files. Okay. We use these kind of files not to store information on our secondary storage, but we use these kind of files to communicate with input-output devices such as terminals, printers, and networks. Okay, you open a file, but that file is not connected to your desk. It is connected to an I/O device such as your network device or a terminal or printer. Okay, so character special files and block special files are usually used for the modeling disks. Okay, so in this chapter when I say file, usually we will talk about this regular files and sometimes directories, and we will talk about these the last two that I marked with green. Okay, in the I/O chapter, next chapter. Good. How about the synchronization problem this morning? Are we having the same amount of synchronization? Is it the same, different, improved, bad? Ahmet, you're here and you didn't talk? Usually Mustafa has some problems. Mustafa, is the synchronization okay? Mustafa, are you there? When I say Mustafa, the captioning, online captioning tool makes up something. Mustafa. Most of our it says. Mustafa. Okay, it makes up something. Okay, that's better than nothing. Okay, Mustafa, are you there? No, you are not. Well, okay. I guess people are. Mustafa is typing, not typing. Anyway, it looks like either this thing is not working at all. Only I am talking to Ahmet Yasir. Okay, 3 people are saying okay. So maybe they kind of solved it. Maybe they kind of solved it. Or people found ways of dealing with it. And I am trying to be careful about not to skip too fast, not to make very sudden moves. Okay, so Ilhan is good too. Good. So let's move on. Depending on the file type, the content of the file, of course, will be different. And that structure, the file structure in the file, depends on the application. Okay, good. So it is improving. So that might be because we have less than 70 people. I mean, it used to be more than 100 people sometimes. So with this smaller number of people. Okay, good, thanks. So let's look at the structure of some of the file types. On the left, I have the executable file. On the right, I have the archive file. Again, the types, the structures of the files changes from system to system. On the left, let's look at the executable file structure. And as I said, this is, I think this is from a Unix file, executable file. At the beginning, I have this magic number. Okay. What's the magic number? Magic number is just something like a, let's say, 34-bit random number. Okay. And this random number is the same for all executable numbers. So by coincidence, it is very difficult to get this number at the top of different file types. So if you are an executable, you use exactly the same number all the time. So the operating system recognizes you as a executable number by looking at this executable file, by looking at this number. After this number, let's say maybe I have 34 bits for the text size and the data size, special kind of data, BSS, so uninitialized data, my symbol table, my entry point, etc. Okay, so this structure is decided by the operating system. This is how the Unix executable files are structured. And the second one is the archive file, which is used for long-term storage of the data. Okay, so it looks like at the beginning I have a header, module name, date, owner, protection size, then the module itself, then header, then module, header, module. You remember this archive files, right? .rar files, archive files. Okay, so this is different. So Ahmet has a question. So Ahmet, he heard me and he's asking a question. Good. Why do we have both extensions and magic numbers then? Are they both identifiers? As I said before, for some systems, extensions are not, doesn't mean anything. They are uninterpreted. For Unix, for example, for Linux, extensions are not important for the system, right? I mean, you don't have to have a file with a extension of, let's say, execute, let's say, let me find a good name. Okay, my prog.exe is the name for executable, in the Windows environment, DOS environment. Okay, you may have the same name for the Linux environment for an executable, but you don't have to have it .exe. Okay, myproc by itself is a good executable name. So how would you differentiate an executable from a C file then for the operating system? So Unix doesn't depend on the extensions. It depends on these kind of magic numbers. Okay, it depends on these kind of magic numbers. So for the DOS environment, maybe that magic number is not there. I don't remember. But for the Windows, it is there. But I don't remember the DOS environment. Maybe that magic number is not there, but DOS makes a decision by looking at the extension only. Okay, so as I said, we are talking about very, very generic rules here. We are not talking about a single operating system. Or worse yet, when I say Windows, there is no single Windows version. I mean, the older version and the newer versions. In the older versions, extensions are not important. Are important for the newer versions. They are less important, and etc. Okay, and these are the two types of file access methods: sequential access and random access. Okay, with the sequential access, you read your file one by one, either bytes or records, in order from the beginning to the end. For the random access files, you may access to any record or byte as you like, as long as it's a valid address. Okay. For some secondary storage devices, sequential access is the only way, like the tape drives. But for disks, hard disks, or SSDs, okay, random access could be done any time that you like. Okay, so we already know these. File attributes, sometimes some people call them metadata. Okay, some people call them metadata, or some people call them file attributes. Files contain data, right? How about the data about the data? I mean, I have data, but I need to have some data about the data. What kind of data? For example, the date and time of the file. Last time it was modified, it was created, it was read, it was referenced, it was moved, and etc. Or the owner of the file, or the size of the file. So these are the information about the file itself. Okay, so these are called the attributes, and attributes are managed by the file systems, and we need to deal with them. File name is just a file attribute, you may say. Okay, file name is just an attribute of the file, which might be the most important attribute, but yeah, it's an attribute. Good. Okay, and there are some attributes that are very common among the file systems. Your file system may not have some of these. Some of them may not be relevant. Some of them are very, very old. But usually, protection is an attribute. Who can access the file? I mean, for the early personal computer operating systems, there was no protection. Everybody could see everybody else's data. Also, very early tape drives in the first generation computers, there is no protection because you do batch processing. Only one program can work at the same time, etc. Sometimes you protect your data with a password. It is possible for some file systems. Creator who created the file, current owner, read-only flag, hidden flag, system archive flag, ASCII or binary. We don't do this with the Unix environment actually. Okay, random access flag. Can I do it sequential or random access? Again, I don't see it with the Unix or Windows. Temporary files, they are important. Lock flags. Okay. Once I locked it, it cannot be moved, and etc. If my file has records instead of bytes, then I need to keep my record length, the key position, key length, and etc. So these are different attribute types, and not all of them have to be supported by all the file systems. Some of them are supported, some of them are not supported. That's why, let's say file system 1 supports this attribute and file system 2 does not support it. If I copy a file from file system 1 to file system 2, then I will lose that data, right? When I copy it back, that data will not be there. So this is what happens if you copy files between different file systems. For example, if you copy a file from Unix environment to the Windows environment, or the Apple environment to the Windows environment, or Android to Windows, and etc. Sometimes you may end up having some weird structures. Okay, that's because not all file systems share the same file attribute set. Okay, good. It looks like I am out of time for today. Okay, let me stop here, and tomorrow I will continue from this position if I don't have any questions. Are there any questions? Okay. Okay, I will see you tomorrow then. Thank you, Fatih. Okay, see ya.